Good morning, everyone. It's still morning. Today we're doing session 2 on electric potential. We're doing questions 11 to 20. Now, you don't need to be that hung up over the question numbers themselves, but the questions, okay? So you need to focus on the questions, not the numbers themselves. So, without any further ado, I'm going to get into the session. Now, the session mostly deals with electric potential energy and electric potential in general. Now, this is my notes. I'm just straighten it out here. Question number 11, okay, is as follows. They tell us three charged particles are positioned in the XY plane. Okay, so this is question number 11. Let me just move that away right there. Okay, now I have lower the thickness. Okay, that's better. Okay, so question 11, we have three charged particles and they are positioned in the XY plane. Okay, so let's say this is the XY plane, or let's rather draw the XY plane and not say these. So this is the XY plane. Okay, we normally have Y and then X, so that's the XY plane. They tell us there's a 50 nanocoulomb charge at Y is equal to 6 meters on the Y axis. This is the Y axis, at 6 meters. There is a 50 nanocoulomb charge, 50 nanocoulomb charge on the y-axis, a negative 80 nanocoulomb charge at x is equal to negative 4 meters. So here at negative 4, that is at 5, this is at negative 4, on x to negative 4, there is a negative 80 nanocoulomb charge on the x-axis and a 70 nanocoulomb charge at y is equal to negative 6. So where y is equal to negative 6, here there is a 70 nanocoulomb charge. 70 nanocoulomb. So this is the situation. We have three charges set up like that is shown in the drawing. What is the electric potential relative to 0 at infinity? So we're taking at infinity the electric potential is 0, and if you were to use the derivation, you would see why that is the case. So we need to find the electric potential at a point x equals to 8 meters on the x-axis. So where it is 8 meters here, okay, let me rather use a different color to indicate this is where we want. This is at 8 meters on the x-axis. At 8 meters on the x-axis, we want the electric potential at that point due to these charges. Okay. Now, how do we calculate electric potential? How do we calculate electric potential? It's easy. Electric potential is equal to V equal to, let me rather see, check here. Okay, so you won't be able to see that part. So let me write it on this side. V, this is electric potential formula, is equal to K times the charge over R. Okay, do not confuse it by squaring this. If you square this, it's no longer electric potential, it becomes electric field at that point. So do not square it in this case. This is what I told you earlier on, how you get it. So first of all, before we continue, we are going to need R, the distances between all of these charges. Okay, so the distance between all of these charges. So the 50 nanocoulomb is the first charge we put down. So let's calculate the distance between that charge and 8. Okay, of course we are going to be using Pythagoras' theorem. Okay, so the distance there, we're calculating this distance here between these two points, the charge and that point. So The distance on the x-axis is 8, while the distance on the y-axis is 5. So that distance there is going to be equal to the square root of 5 squared plus 8 squared. 8 squared is 64, 5 squared is 25. 8 squared, am I counting correctly? Let me just check. 6 meters. Okay, sorry. This is a 15 and a column, but it is 6 meters on the y-axis. That is why it's wrong. There should be a 6. It's 6 meters on the y-axis. Sorry. So 6 meters. So then a slight adjustment there. Let me see. The distance therefore is then 6 squared plus 8 squared. And that gives me the square root of, that's 36 plus 64, that's 100. So the distance is 10. Okay. So 10 is the distance between those two. So the distance there is 10. So that distance is 10 meters. Now the distance between this charge, the 80 Newton charge, and that, you just simply add those distances. They are both on the x-axis, so it would be 4 plus 8, which is 12. Okay, so the distance between those two is 12 meters. Okay. And then final distance here, it's exactly the same. It's 8 there, but negative 6. But since you're squaring, the distance will be 10 as well, 10 meters. Okay. So the distances are, for the 50 nanocoulomb charge, 10 meters. For the 80 nanocoulomb charge, it's 12 meters. And for the 70 nanocoulomb charge, it's 10 meters. Okay, you can work this out on your own. This is just basic algebra using Pythagoras theorem. So now we have the distances. Let's calculate the potential due to each one of these charges. Okay, let's call this charge number 1, the first one we put down, or first one mentioned, charge number 2, and this is charge number 3. Okay, we've already established that for charge number 1, let's calculate the voltage. V1 is equal to K Q over R1, and we've already determined that R1 is equal to 10 meters. So this is 9 times, I'm fond of using 9 times 10 to the 9. Instead of 8,99, I always just round up. And the charge is 50 nanocoulomb, so 50 times 10 to the negative 9. And the distance, of course, we calculated it to be 10 meters. I usually don't write the units in while I'm writing the sum down, but you need to do that. Not need to write it down as you're doing, but the end answer or the resultant should always have its units. Okay, so it's 9 times 50. 9 times 50, that's 450, which gives us, divided by 10, that's 45. So 45 volts. Okay, so the potential due to the 50 nanocoulomb charge is 45 volts. For the second 80, is it the 81? Yes, it's the negative 80. V2, same formula, KQ over R2. Remember the second distance we worked out it was 12. Okay, this is 9 times 10 to the 9. You multiply that with negative 80, which is the charge. Remember, in this case, you need to include the signs, negative 80, over the distance we've worked it out is 12. And that gives us 9 times 80. That's a, first of all, it's a negative answer. 9 times 80, that's 9 times 8. 8 nines, that's 90. Minus 8, that's 82. Divided by 12, should be in the region of 60. Negative 60 volts. Let's just check quickly. I'm going to check. I just want to make sure because I did this in my head. Let's just go to a calculator. Desmos. Usually I just made the screen bigger, so because usually I do have the calculator there. So it will be 9 times 80. That's 772. Sorry, I was wrong. So it's 72 divided by 12. That is 60. Yes. Okay, so back to the questions. So we have the potential, the electric potential due to charge 1 is 45, due to charge 2 is negative 60 volts. What is it due to charge 3? So it is the same formula, KQ over R3. Remember R3 is also 10. K stays the same, 9 times 10 to the 9. And then it's a 70 nanocoulomb charge. So we have 9 times 70. That's 9 times 7 divided by 10. I'm going to check. 9 times 7. That's 63. Yes. Okay, so 9 times 7 is 63. That one on top should be 630 divided by 10, which will of course give you the 63 volts. Okay. Now, remember, they wanted the potential due to all of these charges at that point. At that point, 8 meters on the x-axis. So, the total electric potential at that point, the total electric potential at that point is equal to the sum of the individual electric potentials. So, it will be, what was it, 45 volts plus, I remember this one is a negative, is it 60? Here's my notes. It's negative 60, yes, negative 60 volts. And then you add the last one, we just calculated it to be 63 volts. So there we have, okay, it's not showing up on the screen there, plus 63 volts. So it's 45 minus 60, that is 3 plus 45, that's 48 volts. So the electric potential at that point is 48 volts. I hope that you've been able to keep up with my train of thought. Okay. Question number 12. Let's look at what does 12 expect of us. Okay, what do we need to know? So takeaway from this question, the takeaway from this question is you need to know that electric potential is equal to K coulombs constant. Electric potential is equal to K coulombs constant multiplied by the charge. This is the electric potential due to a singular charge. Okay, so it will be electric potential equal to K coulombs constant multiplied by the charge in question, the charge on the particle, divided by the distance that you want to calculate or you want to calculate or experience the electric potential at. Okay, and that's always relative to infinity, which is 0. Now, and then of course you need to know that the total electric potential at a point is equal to the sum of the electric potentials at that point. So the sum of the electric potentials at that point. That's a good question. We're moving on. And let's just check 48. Check. Yes, there is a green, what do you call this? Tick, a green tick next to 48. Positive note. There are some of these answers could have been negative, okay? Because potential, as you see with the negative 63, can either be positive or the negative 60 rather, that it can be positive or negative. And there it is. The correct answer is positive 48 volts. Question 12. Four charges of equal magnitude are placed at the corners of a square that measures L on each side. So we have a square, four charges. So we have four charges. It's question 12. We have four charges at the corners of a square that measures L on each side. So this square has a length of L on each side. And just for fun, because I think somewhere we might need it, let's calculate the distance between the diagonal charges. It'll be the same for these two and these two. So that distance would be the square root, or rather L square root 2. And if you don't know how we got there, that distance there would be square root of L squared plus L squared, which will give you 2L squared, which is the same as saying L square root 2. That's the distance of the, or the length of the diagonal. Okay, L square root 2. Now they tell us that these four charges are on the square, right? And there are only two positive charges. There are two positive charges plus Q diagonally across from one another. So this would be plus Q. This would be plus Q. And two negative charges at the other two corners. So negative there and a negative there. What is the net potential energy in terms of Q, K, and L associated with this configuration of charges? Okay, let's just look at the drawing. So they have exactly the same. Okay, that's positive and negative and positive. Okay, let me see something. Does my cursor show up? Oh, no, it doesn't. Okay, that I can see. Okay, so we've drawn the situation. They want the electric potential, the net potential energy. Now, what is electric potential energy? How do we calculate electric potential energy? Okay, how do we calculate electric potential energy? It's relatively easy. My notes. So, electric potential energy, which we denote by U, in this case, you can use any value, whatever the one you've been taught. Electric potential energy is equal to Coulomb's constant times the two charges, Qi, Qj, over the distance between the two charges. Okay, that is how you calculate electric potential energy. Okay, Coulomb's constant multiplied by the product of the two charges divided by R. Okay. Now, how do we calculate the total electric potential energy? It is just the sum of all the electric potential energy pairs. Okay. In this case, let's just check something out. It will be all the unique electric potential energy pairs. Okay, let's just note quickly. Let's call this charge number 1. Okay, we will refer to this one as charge number 2, charge number 3, okay, let me rather row clockwise, charge 3, and charge number 4. Okay, let's not go into Q at the moment, what it's called. Let's just name them like that. Now, I want to know how many unique pairings of charges are there. Okay, so there's 1 and 2 plus there is 1 and 3, there is 1 and 4, there is 2 and 3, there plus there is 3, 2 and 4, and then there is 3 and 4. Okay, you can switch them around, but you'll see each one of these is a unique pairing of charges. It doesn't matter which one is in front, 1 or 2 like in this case, but as long as it's a unique pairing, you won't see any other pairing of a 2 and a 1. Charge number 2 and 1 is in the setup. So what this tells me is that there is six six original pairings of charges. Okay, if I were to say 2 and 1, that's the same as 1 and 2. Okay, so there's six distinct charging pairs or charge pairs. Okay, you can call them whatever you want. Okay, now the total energy would be then the energy of these six pairs of pairings, or these six pairings rather. Okay, let's say. Okay, so total energy of that configuration would be energy to, oh, it's terrible because I can't. Let's try this and see U. Okay, U total. Let me see if it shows up there. U total is equal to the energy from 1 and 2 plus the electric potential energy of 1 and 3 plus the electric potential energy of 1 and 4 plus the electric potential energy of 1, or rather 2 and 3 plus the electric potential energy of 2 and 4 plus the electric potential energy of 3 and 4. Look how I wrote this. Okay, you'll see there's a pattern. Okay, this is charge number 1 whatever all the other charges. This is charge number 2 with all the charges after it, and this is charge number 3 with all the charges after it. Okay, so then if we were to calculate this all, okay, for each individual pairing, okay, it's K. Remember, all the charges are Q. Okay, in this case all charges are Q, and we've named them, or rather we have given them numbers. Okay, so this one here in the upper left hand corner is number 1. The one next to him, let's just recap. This is number 1, this is number 2, this is number 3, this is number 4. That's how we name them, just to make our lives easier. Okay, so just keep that in the back of your mind. That's why I wrote it like that. So we have now the charge pairs, the unique charge pairs. Let me just erase that. So we have K, Q. Remember, each of those charges is Q. What the only difference is that one is a negative and one is a positive sometimes. Okay. Now let's look at the first one. Okay, let's look at the first one. The first 1 and 2. Okay, 1 is positive and 1 is and 2 is negative. So the value up front, the sign will be negative. It's charge multiplied by, remember, electric potential energy is equal to K Q1 times Q2 over the distance between them. That's the electric potential energy. Let me rather not say Q1 and Q2. Let's say Qi and Qj over the distance between I and J. Okay, that is the formula. Can see that. I write it here. Electric potential energy is equal to K times Q1, Qi times Qj over the distance between R and J, between I and J. Okay, that is how you get electric potential energy. Change it. I'm going to leave it up there. So the first two charges, they are both Q, so it's Q times Q, so it's Q squared, and it'll be Q squared for all of them because they're all just capital Q. So it's Q squared. What is the distance between those two? It's L. Then it is 1 and number 3. They are both positive, so it will be a positive. So it's K, it's Q times Q, so it's Q squared. The distance between those two, we worked it out at the very beginning, is the square root 2 times L. Then it's Q1 and 4. It is a positive and a negative, so it's negative K Q squared will always be there. The distance between them is L. Then it's charge number 2 and charge number 3. It's they are both, one is positive and one is negative, so it's a negative. It's KQ squared. The distance between them is L. Then we have between charge 2 and 4, it's both positive, so it is KQ squared over the distance between them is square root 2L. And then the very last one, it's between 3 and 4. The distance between the charges are both, one is positive, one is negative, so it's a negative. And the distance between them is L. It's KQ squared. So there we have all the distinct charge pairings. Okay? So now we just need to take out a common factor, which in this case is KQ squared over L. And if we were to take that out, now I'm going to leave that up. You can go and pause there and take it out yourself. So I'm going to take out KQ squared right here. KQ squared over L is a common factor. What we're left with is negative L plus 1 over square root 2, negative 1, plus 1 over square root 2, negative 1. Okay? Wondering if you can see that. Let me just go back. Negative 1 plus 1 over square root 2, negative 1. Now if you were to summarize that or clean it up a bit, negative 1, negative 1, negative 1, negative 1, that's negative 4. And then plus square root, plus 1 over square root 2, plus 1 over square root 2, plus 2 over square root 2. Okay? That would be the electric potential of this entire system of charges. Now let's check if there's an option for that. Nope. There's a negative plus 2 square root 2 kq squared, negative 4. There's that one, but it's a positive 4. Let's try the one number B. Let's check. The correct answer is, yep, it is the one that we chose and worked out. Question 13. Let's check question 13. Identical 2-micron charges are located on the vertices of a square with sides that are 2 meters in length. Okay, so again, we have a square, but in this case, they tell us that the side length is 2 meters. So we have a square, 13. We have a square with charges at the vertices. There are charges, that means at the corners. And each length of the square is 2 meters. Now, if we were to work out, they ask us to determine the electric potential relative to zero, which is at infinity, at the center of the square. So we need to determine the electric potential at the center of the square. First of all, let's calculate the distance to the center of the square. The diagonal distance would be just, let's call it d, the diagonal distance d. D is equal to 2 square root 2. So the 2 squared plus 2 squared, that will be the diagonal distance. And that is equal to 4 plus 4, that's the square root of 8. That's the square root of 2 times 4. So 2 square root 2. So that's the diagonal distance. But we want the distance just from each vertex to the center. So it will be half the diagonal distance. So if we half that, okay, we get just square root 2. Okay, so the distance therefore from a vertex to the center is just square root 2. Okay? The distance like that is just square root 2. So we haven't even gotten to the problem yet. We've just determined the distance to the center. It's square root 2. Let's call it big D. Distance to the square root 2. I should have rather called the diagonal distance big D and then half that small d. But let's say that distance there is small d. Okay, let's refer to it as small d, and it's square root 2 meters. That's about 1.41 meters. Okay, now they want determine the electric potential at that point. Okay, now you need to determine the electric potential for each one of these charges. Now these charges are identical, so if you determine the electric potential due to this one charge, you can multiply it by 4 and you have the electric potential for all of those charges at that point. Okay? Now remember, electric potential is a scalar, so they won't cancel out. So let's calculate the electric potential for one charge. Like we said in our previous problem, electric potential is equal to K Q over R, and then we have that K is 9 times 10 to the 9. Q is 2 nano. Is it 2 nano? 2 microcoulomb. 2 times 10 to the negative 6. Nope, it doesn't fit. Remember, I'm checking on my YouTube setup here. So that's equal to 9 times 10 to the 9. Excuse me, I almost wrote negative 9. Multiplied by 2 microcoulomb. 2 times 10 to the negative 6. And there we have it. The distance between that, from that one charge to the center, is square root 2, and that gives you a voltage, if you work it out, of 1, 2, or approximately around this value. I didn't round or anything, so it's approximately around this value of 12714 volts. Okay, 12714 volts. So you have this voltage at the center due to one charge, but you have in fact four charges, okay, same distance away. So the total voltage, the voltage total, is then equal to 4 multiplied by 12714 volt. That is your voltage total. And if you multiply it by 4, that's 12,714 times 4. You have that your total voltage at the center is equal to around 5856 volt. So 50,000 volts. So 50 kilovolts. So approximately 50. If you round up, you will get approximately 51 kilovolts. So approximately 51 kilovolts. Let's see if there's an option for either 50 or 51. 51 kilovolt is the first one. Let's pick it. Let's check. 51 kilovolt. And yes, 51 kilovolt is indeed correct. So our approach was correct. You just need to get the approach correct. Now, moving on to question number 14. Okay. Which of the following charge distributions has the lowest potential energy? Okay. And we need to then work out the charge distribution for each one of these charges. Okay. And that is quite easy. Let's do it. We've already done uh, electric potential energy in the previous, the question before this one, question 12, I think. Electric potential energy, we stated that electric potential energy is just electric potential energy between I and J is equal to K times the charge at I times the charge at J over the distance between I and J. Okay, so let's calculate it for the first setup. So let's do it for number one, and we're going to write the answers here. Let's write it here for number one. This is going to be our answer. Our electric potential for one. So there are two charges for number one. That is two Q charges. So U is equal to K Q times Q. So that's Q squared over the distance between them is 2A. So this is the electric potential due to two charges. Okay, it is K Q squared over 2A. That's for two charges. Let's look for. Okay, let's do it this way. Process of elimination. Okay, we want the lowest. The lowest. So far, the lowest is number one. Let me rather, I'm going to confuse some people. So keep that in the back of your mind. The first one is KQ squared over 2A. Let's do it for number two, or rather setup two. Okay, where is it? Setup number two. I'll move it into position. It's the setup here, setup number two. So we have three charges now. Okay, and if we work it out, there are then three unique pairings. Okay, it is this charge here. I don't know if you can see that on your. Wondering if you can see my cursor. No, I don't think you can see my cursor moving. Okay, so it is the, oh, you can. Okay, so it's this charge here, and this one, and then this charge, and that one, and these two. So there are three unique pairings. Okay, so let's add them up. For the first pairing, it is the positive and the negative. The positive on the left and the negative charge. So it will be potential energy is then K, and then it's negative because it's a positive and a negative charge. All of them are Q, so it's Q squared. And the distance between those two, between this positive and the negative charge there, the distance is A squared plus A squared, that's 2A squared, and then the square root of that is A times the square root of 2. It's like the previous question. And then the same exact answer will be for the pairing between the negative one and the other positive one. So it will be k q squared over a square root 2, and then plus, then between the two positive charges themselves, it'll be k q squared over 2a. Okay, now if we were to take out a common factor, that'll be k q squared over a, which is the same as we had before. Between those two, k q squared a was taken out, but in this case you multiply it by, that's a half minus 1 over square root, or rather 2 over square root 2. Right? And that is basically k q squared over a multiplied by approximately negative zero point 0.9. So that's a negative value. Okay, so this one has a negative value. The first one was positive. Let's check the third one. This one will be, since all of these charges are positive, okay, all of these charges are positive, it's going to be the same as for number 3. For number 3, the only thing that's going to change is that it's going to become a positive, and that's going to become a positive, and this will now become a positive, meaning this will change. But an overall, this whole system will be positive. Okay? Why don't I write that value down? It's because it's not going to be the lowest. The lowest so far is number 2, okay, which is negative zero point 0.9. Okay, times that value. We need to get something that's going to be lower than negative zero point 0.9 times kq. That's the one to beat, because we want the lowest of all of them. Okay, so far number 2 is the lowest. Let's check number 4. Okay, now if we were to work out number 4, or first of all, let's go to number 5. They are all negative, but if you multiply q by q, negative q by negative q, they will all become positive. So it cannot be number 5 either. So it is between number 2 and number 4. So let's work out the electric potential due to the setup in number 4. Due to number 4. Okay, so we can already work out, or if you want to, you can work out the same setup as we did in 4, and then just add each one of them with the new additional charge. So what you do is you take the one that we had for number 2, and you add it, you then combine each one of those charges with the one at the bottom that has been added. So the one for number 2 was kq squared over a, that looks like a 9, over a multiplied by negative zero point 0.9, and then you add the additional charge combinations. Okay, that is both of those two positives, the one on the left and the one on the right. You add them, so it's kq, so it's 2kq squared. No, let me rather just write them. I can't do that. So it's kq squared over, it a square root 2 plus k for the other one, kq squared over a square root 2, and then minus, of course, the negative one on top, so it's 2a, and that gives you, let me see if it's still fitting in, minus the one on top, it's k q squared, okay, 2a, because the distance between the top charge and the bottom charge is 2a, and working that out, we get kq squared over a plus, if we take kq squared over a out here as well, that's times negative zero point 0.9. Let me just rewrite that. Negative zero point 0.9, that's 0.9 plus if we take kq squared out of these three as well, q squared over a, we have that is 1 over square root 2 plus 1 over square root 2 minus a half. Therefore, if we rewrite it, we have kq squared over a negative zero point 0.9 minus zero point 0.5 plus 2 square root 2. And that, ladies and gentlemen, gives you a positive value, if I'm not mistaken. Or rather, let me see. No, that should give you then a positive square root 2.9. It should give you zero point 0.9. 2 square root 2 should be zero point 0.4 then. Let me check. That is approximately zero point 0.9 minus zero point 0.5. That's 1.4. 2 square root 2 should be 1.4 around there. Let me check. 2 divided by square root 2. My math is not failing me. Yes, it is 1.4. So this answer will be 0 if you were to work out the whole thing. Therefore, the smallest combination of potential, electric potential, is number 2. Okay, the electric potential combination with the smallest electric potential energy is number 2, is D. So let's click and check. Yes, indeed, the correct answer is number 2. Remember, you had to calculate the lowest potential energy, and we've calculated electric potential energy for each of those setups. We immediately discounted those that would be positive without calculating it because we wanted the lowest, which means, and we already had a negative. Okay, so all of those that would be positive, like number 1, they have all positive charges. Number 3, all positive charges. Number 5, all negative charges. So if the charges are all the same, the electric potential energy would be positive. Now we just have to calculate for number 2 and number 4. And if we work it out, the electric potential energy due to the configuration of number 4 is exactly 0. Okay, because each one's contribution would be cancelled out. And then that leaves us with electric potential energy of setup number 2, which is a negative value, or will be a negative value. 15. Okay, number 15. Rank the potential energies of the systems of charges from largest to smallest. From the largest to the smallest. So we need to calculate the electric potential energy of each of these systems of charges. Okay. So let's do it for A. Let's calculate the electric potential energy due to A. How many are there? There's A, B, C, and D. Okay. For charge number A, setup number A, we have electric potential energy. U is equal to K. It's Q for all of them, so it's going to be Q squared over the top one and the bottom one on the left. So it is going to be, the distance is D. So it's D plus top one and bottom on the right. KQ squared D. And then the 2 on the bottom, it's going to be KQ squared D. KQ squared over D. all are the same distance away from each other. So basically what we can say then, the electric potential of that entire system is just 3k q squared over d. That's the electric potential of that system A. Let's calculate the electric potential of system B. It's the same setup, but just one of them is now negative. Okay, one of these charges is now negative. Right? So we've already calculated for A, it's 3kq squared over D. So let's calculate it for setup number B, the electric potential energy. So we're taking the top one as number one, so it is going to be, or rather we're starting with that one. You can start with any one, or let me rather start with the negative. Oh, I'll rather start with the top one. Okay, so it's going to be negative and a positive and a positive. So it's going to be positive k. I don't need to write the positive, but I choose to. K q squared. The distance between them is d. The next one is negative. It is k q squared over d. The exact same thing. It's only now the sign will change, and then the 2 at the bottom will also be negative k q squared over d. So for B, the setup answer is 2kq squared over d plus kq squared over d. For number one, it was bigger than this one. Okay, so it was just 3kq squared. So what we can say so far is that B is smaller than A. Okay, so we can say that A is bigger than B. So we can say so far that A is bigger than B. This is all we can say so far. C. Let's look at the setup for number C. This is all positive. Now that's an easy way. We have done something like this before, but the charges were oppositely charged. Okay. In this case, there is 6 unique pairings as well. When you have a square, you have 6 unique pairings. Okay. Now I'm going to leave. Well, let me rather just calculate it. There are 6 unique pairings. The electric potential energy is equal to k q squared over d plus k q squared over d square root 2 and then plus k q squared over d. That is the first 3, and the second 3 will be kq squared d, kq squared over d plus kq squared over d square root 2. And then the last one will be between the bottom two will just be kq squared over d. So let's count them up. Kq squared over d, how many are there? Well, there's 1, there's 2, there's 3, that's 4. So it's 4k q squared over d plus 2k q squared over d square root 2. Now this is very big. Okay, so we know now that C is bigger than B, which is bigger than A. Okay. Now where does D fit in? Okay, where does D fit in? If you work out the electric potential of D, you will find that the electric potential of D is exactly 0. And I'm going to leave that, or rather let me just do it. but it's relatively easy. So we will have kq squared over d for number d. So we now know that d, or rather I can just tell, well, at this point I can tell that it's going to be 0. So let me work it out then. The electric potential, energy, I shouldn't say electric potential, I should say electric potential energy of D is equal to K Q squared over D, the first one, plus negative, or rather it should be negative because it's going to be with the negative, K Q squared over D square root 2. That's it. Then we have last one, positive K Q squared over D. Moving on, we have negative K, it's still the same. It's negative K Q squared over D, and then positive K Q squared over D square root 2, and then finally between those two it's going to be negative, let me write it here, it's going to be negative K Q squared over D. And if you add them all up, okay, you will find that there's 2 kq squared over d's plus 2 I must say distance here, there is that one there, d, okay, yeah, I have it. There is one positive, so it should be this one then, uh, kq squared over d square root 2, and then the last one should be a negative. It's those two, 1 2 3, negative 3 kq squared d square root 2. Was it 2? No, 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 no. Sorry, it should not be 3. Let me check. Kq squared over d, kq squared over d, those two are done. Then we're left with negative kq squared, negative kq squared over d, positive kq squared over d. It's this one here. That's negative kq squared over d, negative kq squared over d. That one and that one. They're done, and then we're left with now this should be positive kq squared over d by square. That is right. Negative kq squared over d. I'm missing one. Let me check. That is 1. That's D. That's D square. That's D again. That's D square. Oh, here it is. D squared, yes. Oh, I did not complete. It's D squared. Should be D, negative. dv squared, that's dv squared. Those two will cancel, positive k, negative. Okay, so they two cancel. That one and that one. That's negative kq over d. That's negative kq over d. That's negative 2 kq over d. Okay, right. If you add them all up, you will eventually get 0. I just didn't see the minus. So, it is now 0. Okay, so we have all of them. And if you can remember, we had that C is bigger than A, which is bigger than B so far. Okay, now where does D for D is 0? Okay, we remember that A is positive. Okay, A is positive. A is positive, so 0 is smaller than, let's just check. C is positive. C is the biggest positive. A is also positive, so C, A is bigger than that. Then we have a negative, which is B in this case. B was negative, and then we also have 0. So D will be between A and B. Okay, let me rewrite it then. So it's C bigger than A, which is bigger than D, which is bigger than B. Okay? That's a good question. Nice calculating electric potential energy. C bigger than B, which is bigger than D, which is bigger than A. That should be A. Let's check. Yes. Oh, sorry. Did I pick the wrong one? CADB. 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 Which one did I pick? CB. Oh, I did not need to read. It's CADB. So it should be B. The correct answer is CADB. The one I wrote here, not the one I picked there. Okay. Question 16. Okay. Another nice question. But this one is basically just you need to know how to calculate capacitance. Okay. 16. So, a parallel plate capacitor is made of two metal plates pressed against a thin sheet of dielectric material. Okay? Now, the capacitor is connected to a power supply which provides a potential difference of 90 volts. Okay? So, we have this power supply provides a potential difference of 90 volts. Let's draw this small setup or try to show you what is happening here. We have a parallel plate capacitor. And then of course we have here the second plate. Let me draw it not that way, or rather this way. This is the parallel plate capacitor. We have the 90 volts. This is a simplified setup of what is happening. And the power supply is first disconnected and then the dielectric is removed. There's a dielectric material in the parallel plate capacitor there between them. The power supply is first disconnected and then the dielectric is removed from between the plates, and the potential difference across the capacitor was now found to be 450 volts. So first it's 90 volts with the dielectric, but when they remove the dielectric it's 450 volts. What is the dielectric constant of the material that was initially placed and then removed? Now, The initial charge of the dielectric. The initial charge of the dielectric material initially is equal to the initial capacitance times the initial voltage. Right? The final charge is the final capacitance times the final voltage. Right? That is just charge defined in terms of capacitance. Okay. Now, since the power supply is disconnected, the charge is constant. The charge will be constant for both of them. Okay. So Qi is equal to Qf. Charge remains constant. The power supply is disconnected. So that it just means the initial CVI is equal to CF VF. Okay. Now we have this formula CF VF. Okay. Now we know that the initial capacitance is equal to the dielectric constant. It is a weird K times the initial capacitance. And the final capacitance CF is equal to just C, because the dielectric has been removed. It's just CF is just equal to C naught, what was there originally. Remember? Now if you plug this in, remember the formula we just had? It said C initial times V initial equal to C final times V final. But we've already established that C initial is equal to the dielectric constant times the initial capacitance times the initial voltage. And then the final capacitance is just the initial capacitance because the dielectric has been removed. And then, of course, what you need to understand is that formula, you need to know it, the final voltage. Okay, so going on that assumption, we can plug everything in we know so far. And then, of course, if we divide both sides to get the dielectric constant, this cancels out the initial capacitance, and we have that V final divided by V initial is going to give you the dielectric constant. Right? So the dielectric constant therefore is equal to V final minus V initial. Just some math, so it's 450 divided by 9 with 90 volts. Yes, 450 volts divided by 90 volts. That gives you 35 is 5. So 5 is the calculated value of the dielectric constant. Let's check. 5, check. The correct answer is 5. So a circuit contains a 3 microfarad capacitor. However, a technician decides a 4 microfarads of capacitance is needed. So it has a 3 microfarad capacitor initially, but the technician decides, we need 4 microfarads. What size capacitor should he add to get 4, and how should it add? Should it be series or in parallel? Okay, let's check each one of them. 12 microfarad in series. Let's check if it's in series. We can check each one of them. These are options. Okay. So 12 microfarad in series. So we have initially a 3. So if we have 3, let me just. So we have 3. We add another one. We have the 3. We add the other one, 12 in series. How do we add capacitance in series? It's equal to 1 over 3 plus 1 over 12. And that is not going to be equal to, so that is 12, that's going to be 4 plus 1, so it will be C is equal to 1 over C there, so C is equal to 12 over 5, and 12 over 5, 12 divided by 5, 12 divided by 4 is 3, so 12 divided by 5 is less than 3, less than 3. The answer is less than 3, but we want it at 4, right? So we can't. So A, it cannot be a 12 microfarad in series, so let's check option B, 12 microfarad in parallel. Okay, so it's that. So that's 3 and 12, that is equal to 15. Okay, because we just add them up. That will be 3 plus 12, that's 15 microfarad. So it can't be B. Let's check if it's C. 1 microfarad in series. Okay, so we have 3 still. We add 1, so it's 1/3 plus 1 over 1. It's 1 over C. 1 over C. So C is equal to 1 over C is equal to 3, 4. So C is equal to 3 over 4, 3 quarters. Right? It's not that one. We want it is 4. So it can be 1 farad in parallel. Okay, so we have 1 microfarad in parallel. So that's 3. Remember, we want the answer to be 4. That's 3. That's 1. If we add them up, we get 4 microfarads. So option number D is correct. If we add 4 microfarads in parallel, we have 7. Okay, so let's check. The correct answer is 1 microfarad in parallel. So that's just, they want to see if you know how to add capacitance. 18. Assume you want to increase the maximum operating voltage of a parallel plate capacitor. This is just your knowledge. With a separation between the two plates fixed, which of the two following may help if you want to increase maximum operating voltage? Remember, the voltage C times V, but we also know that is what we've gotten so far. But we also know that voltage is equal to the dielectric. I'm not going to write it out. We also know that voltage is equal to a product of the dielectric strength and the material's thickness. Okay. So if you want to increase the operating voltage, okay, you can, number one, evacuate the space between the two plates. Okay, because air has the highest, I think, the lowest dielectric constant. Air has a very high electric constant. I think dielectric. Then put a material with a higher dielectric strength, you can, yes, than the one you have already. Reducing the area of the plate is not going to help, and then putting a material with low is not going to help. So let's check those two. Yes, you can put a material with a higher dielectric strength, and then of course evacuate it because a vacuum has highest dielectric strength. 19. Those are all theory-based questions. If you study enough, you can get it. What is the equivalent capacitance of the combination shown when C is 15? So let's just note C is 15. Let's just calculate the equivalent capacitance. Now for the capacitance in parallel, we have 1 over C plus 1 over 2C plus 1 over C. Oh, sorry. That is for, I'm thinking of resistance now. In parallel, capacitance in parallel is just equal to C plus 2C plus C. That's 4C. So they in parallel it is 4C. Okay. Now we need to add that in parallel to the one in series. So capacitance in series is 1 over S equal to 1 over C plus 1 over 4C that we've just calculated. So that is equal to 4C. Where's my, okay, there we go. I'm just checking now. Am I doing that C? Let's see. They should be that parallel. It's 4C. Okay. Checking something that's 5C. 5. Mm-hmm. We flip it over. It's 4 divided by 5. So 4C divided by 5. 4 times 15 divided by 5. There it is. 4 times 15. That is 60 divided by 5. And 60 divided by 5 is 12 microfarads. Is it microfarads? So 12 microfarads. So yes, I did do. I was just checking now, did I include this one? That's why I did it that. So yes, I did include it. It's 12 microfarad. Final question of today. Each capacitor in the combination has a breakdown voltage of 15 volts. What is the potential drop between A and B? So the potential drop between A and B of the entire combination. Okay, so let's first, if you want to do that, you first need to calculate the equivalent electric capacitance. And it's reasonably easy. We have one in parallel, two sets in parallel. So it is, if you were to draw it again, you have the following. Remember, here you have still in the middle the 10 microfarad capacitor. These two are in parallel, so you just need to add them. So that's 40 microfarads. Same with the other one, it's 40 microfarads. You just add them. So the total equivalent capacitance, therefore you can then calculate. So you have the capacitance as 40 microfarads and 40 microfarads from the parallel combination. But we are not done yet. We want the potential drop or the voltage drop between A and B. Now the easiest way is to just put points in between. Remember, this is uh, that's A and B, so let's call this A, yes, and it's B. But let's mark this point here as C and that one as D. Okay. So we can calculate using the voltage drop across them. We can calculate the charge. Now the voltage drop between A and C is equal to, we have the capacitance and we have the voltage drop across them. The voltage drop between those two is the same as the voltage drop between those two, CD, which is the same as the voltage drop between DB. Okay? What is it there? Each capacitor in the combination as shown has a breakdown voltage of 15 volts. Okay, so we have 15 volts across all of them, or rather the charge in them is the same. The charge in all of them is equal to the voltage. What is charge again? Charge is voltage times the capacitance. Okay, so the capacitance there, the capacitance for the 40 microfarad, 40, and then we have the 10 microfarad times that VCD, and then we of course we have the other 40. Therefore, the change, if you were to work it out, you can cancel the 40 then throughout. You will get that the voltage between C and D, which is at 15, is equal to 4 times the voltage between AC, equal to 4 times the voltage between D and B. That's the easiest way I can figure to do this. Of course, there are other ways. Now you have that. The center capacitor will break down first at 15 volts. Now when that, those are the breakdown voltages, remember? Now the voltage for the center one, V, remember it's going to break down first because we just said that voltage of, is it AB or AC rather, that we just wrote down, is equal to 4 times the voltage of AC is equal to the voltage of CD is equal to the voltage of dB. Okay, 4 times dB. The first voltage is going to break down is that one. Okay, voltage it's going to break down is that one. CD. Okay, now I just rewrote. I'm just looking at my notes. I started from the other side, so that one is my A. I reversed them. Okay, so the first one is going to break down. Okay, so the voltage between A and B, the whole setup, or rather, not the whole setup, we do it step by step. Let's still do step by step. So AB, CD, so it's going to be AC in my case here. The voltage, the change in the voltage between AC and dB, the change in that voltage between AC and the change in the voltage between dB is going to be equal to a quarter of the voltage between BC, or in this case CD. Let's see if it's showing quarter of the voltage between B. Okay, so and And that voltage there, CD, is just a breakdown voltage, which is 15. So a quarter of 15. What's a quarter of 15? It is 3.75 volts. So the change in that is 3.75 volts. So the voltage between points A and B is going to be equal to the voltage between the first one, 3.75 plus 15 plus 3.75. Remember, because those two are the same, so it's going to be 3.75 volts plus 3 plus the 15 in the middle plus 3.75. And that's approximately 22.5 if I'm not mistaken. And there you have it, ladies and gentlemen, 22.5. Let's check. Correct answer is 22.5. And that's all that we're going to do today. Have a great time studying and all the best.